Is Dr. Tim Wise, pronouns he, him. Dr. Wise is industrial professor in the mechanical engineering at the University of Alberta. His research focuses on renewable energy development and energy storage, particularly related to wind energy. Tim worked for the Pembina Institute and the Canadian Wind Energy Association, as well as an advisor to the Alberta Minister of Environment and Climate Change. So Tim, please welcome, and please share your screen.
So I'm going to shift gears, and I'll try to introduce the idea of how does the electricity that we consume get to us when we flip the switch. Now, most of us probably don't spend a whole lot of time thinking about what goes on when we flip the switch. Maybe that occurs to us when we flip the switch and the light doesn't turn on, or maybe when we go to pay our bills. But I'll leave that component of the discussion to the next speaker, Dr. David Brown, to talk about the price that we pay when we do flip that switch. But for the most part, when we flip the switch, the lights come on, and we're happy to have that electricity. But we don't often think about what's going on behind that switch. And in fact, there's actually a whole lot of complexity behind our wall. So I'm going to try to answer some of the question of where does our electricity come from, with a focus on Alberta, but also briefly touch about what's going on, or where does it come from in Canada? How do we get it? What's the scale of that system? And electricity used to be a fairly sleepy sector, but it's probably one of the more exciting energy sectors these days because it's changing really, really rapidly. And so we'll talk a little bit about some of those changes that are occurring and what opportunities there are and challenges as well. So first question then, if we want to think about where does our electricity come from, we need to almost take a step back and ask ourselves, well, what is electricity itself? And so first off, electricity is a form of energy, but it's not just any form of energy. It's an incredibly versatile form of energy. We can use it for all sorts of different uses, and it's from powering our computer to running an electric car to turning on lights or to heating our home. So there's an incredible breadth of things that the electricity system can do, or electricity as an energy form, I guess I should say, can do. And in fact, it's so useful. If we look over here on the right-hand side of my slide here, electricity is about 17% of our overall final energy consumption in Canada. So it's one of the most important sources of energy that we have overall. But sometimes when we report energy data, energy consumption data like this, it actually underplays the size of the overall system or the importance of the electricity as a sector. And we'll get to that in a minute. But the reason being is that electricity is what we call a secondary form of energy. And so we don't just find it, we don't mine electricity, but we have to go out and we have to create it. And so we need to start with an initial energy form, what we call a primary energy form, and convert it into electricity, which ultimately we're going to consume. And unfortunately, along comes our friend, the second law of thermodynamics, that tells us every time we change energy from one form to another, we're going to lose some of that energy along the way. And so when we consume that electricity, we've ultimately has had several types of energy conversion that have gone on behind that and meant that we've lost some of that energy along the way, which ultimately means we've actually consumed more energy in the overall system. So it does mean that there needs to be more primary energy that gets put into the overall system compared to what we're going to finally consume. So let's then think about, okay, well, what all are the different pathways that we can use in order to get electricity to us? And so I started out trying to make a very simple diagram here, and it got a little bit ugly. But the good news is really we have two distinct sources where we ultimately generate electricity from. Uranium and sunlight, and sunlight really being the dominant one. And the sunlight, of course, can take all sorts of different paths in order to get converted into electricity. If we can convert sunlight directly into electricity through the use of photovoltaics, and that's probably the most direct conversion and the quickest, but it's not the one that we use the most, at least these days, in our overall system. In Canada, we tend to use a more indirect path of sunlight, where the sunlight takes some of that, the energy hits the earth, it moves some fluid around, so it moves liquid up a mountain, and then it flows down through a stream, and we convert that into kinetic energy to run through a hydro dam, or it moves the atmosphere around, and we use wind turbines to extract that energy. So we have, again, we've got sunlight turned into kinetic energy, which then we turn into electrical energy. But more often than not, we have sunlight, which takes a longer path, and it gets absorbed by biomass, which then turns into fossil fuels, and then we run that through another system to then extract the heat from that fossil fuel, and then run that through a power plant to get ourselves electricity. So ultimately, for the most part, anyway, most of our energy ultimately is derived from the sun itself. In Canada, we have a lot of hydro electricity, but for the most part, in the world, much of our electricity is generated from thermal sources or from fossil fuel sources. So in spite of my fairly complex graph here, for the most part, we're just sort of following this main path here down to the middle. And that's also true in Alberta. So we're taking a fossil fuel, we're burning it, releasing that chemical energy, turning it into thermal energy, turning that thermal energy into kinetic energy, and then that kinetic energy into electrical energy. So there's lots of steps along the way, which unfortunately means that we've lost some of that energy that we started with as a result of making all those conversions or all those changes. So when I flip the switch in Alberta and I consume that electricity, has come to us via a transmission system, and there's going to be some additional losses along the way. But then we also think about all those conversion losses, which I just mentioned to you. And so then if you look at the diagram of the final electricity that we consume here, upstream of that, we've actually had to put a lot more energy into that system overall, because unfortunately, as a result of all those conversions, we end up losing a fair bit of that energy through thermal losses. And some of those are simply inevitable. So there's a lot more going on behind the system in terms of energy consumption than maybe just the final energy that we're consuming in our office or our homes. So what's going on specifically in Alberta? Well, Alberta's in the midst of a massive change in its overall electricity system. It's a really exciting time to be looking at the system in Alberta, because we've gone from a system that was about 2/3 coal just 15 years ago, and is now down to, at the end of 2021, about 20% of our entire energy in the mix came from coal. So that's one of the most rapid conversions of an overall system that we've seen. In fact, the plans are that we'll see coal likely phased out by close to this time next year. And so that's not only one of the most significant decarbonization processes that's going on in North America, but also one of the fastest changes to an overall electricity system as well. So let's look at that then in terms of percentages of where our energy comes from. And so over here on the right-hand side, we can see, again, that transition from a lot of coal historically to being largely displaced by natural gas, as well as some growth in the renewable energy sector combined up at the top here to totaling about 15% of our overall electricity consumption, although the majority of our power still definitely comes from the thermal sector. Now, you might think we really have we still have a long way to go, and that's probably true. There's still a lot more decarbonization that needs to occur in the Alberta electricity sector. But the good news is, going back to what I had said earlier, is that when the more and more renewables that we add on to the system, is they don't have those same thermal losses. And so when the more renewables that I'm adding to the system, if I go back to my diagram at on the left-hand side here, the more that I'm adding on this side, I'm also commensurately diminishing the losses that are going on in the system. And so that means I put less and less energy into my overall system, the more thermal energy that I actually take out of it. So Alberta is a little bit unique in Canada. Alberta and Saskatchewan are a little bit different than much of the other provinces, which overall in Canada, we don't have a majority thermal system. In fact, in Canada, the majority of our electricity actually comes from hydroelectric power. In some cases, some of the jurisdictions are well over 95% of their electricity comes from hydro. And if we include other non-emitting sources such as nuclear power, wind, and solar, our entire system on average is about 80% non-emitting. And we're also, not only is Alberta phasing out coal, but the entire country is, and that should be completed at least by 2030. So we are seeing we are seeing a transition occurring all across the country as well. One of the other major interesting things that's happening, not only in Canada, but around the world, is that renewable energy, which used to be fairly expensive, wind and solar in particular, have now gotten to the point where they're actually some of the lowest cost energy that we can install. And so that's also changing the way we think about what our energy system is going to look like in the near to medium future. And so you may have heard this term, which comes up a fair bit, which is called electrified everything. And the reason that comes up is because of those things which I had just mentioned, that we have renewables that are coming onto the system that are relatively low cost. So wind and solar are now plentiful and low cost. And so if we take those renewables and we start adding more and more to them to the system, we can start to clean up our overall energy electricity system. Once we've done that, then we can start moving some of those other sectors onto the grid. So going back to where I started, electricity being a very versatile form of energy, we can start to not only clean up where we're currently consuming electricity, but we can also start to help decarbonize some of the other sectors in the economy. So whether that's transportation with electric vehicles, or potentially using electricity in heating or industrial processes. As a result, of course, it does mean that we need to expand. We need to not only clean up the grid, but we're going to need to expand it and make it bigger. And so it sounds easy, maybe, to electrify everything and make that transition happen, but there's obviously some major challenges that go on that we're currently facing and currently sort of struggling through, not least of which is scale. So let's go back to the diagram which we started with here on the right-hand side and say, okay, well, our electricity system currently is only about 17% of our end use. And now we're talking about potentially decarbonizing the entire, if you want to electrify everything, now I need to move my refined petroleum products as well as my natural gas system onto the electricity grid. Does that mean now that I need to expand my electricity system fivefold? Well, no, the good news is that we obviously do need a lot more electricity, but our internal combustion engines in our cars are only about between 20 and 25% efficient at actually taking that energy in the gasoline and converting it to kinetic energy, whereas an electric car is closer to 75 to 80% efficient. So the good news is we don't actually need to displace all of this energy here. Maybe we only need to displace, for argument's sake, let's say half of it. And the same can also be true on the heating side of things. That things like heat pumps, for example, can be 2 to 3 times as efficient compared to just even high efficiency furnaces. So maybe we only need to let's be optimistic and say we only need to replace 50% of that system. So it may be that the challenge isn't quite as big as it initially appeared, but it's still huge. The scale of electrification and the scale of change would need to be massive. But some of that is happening, whether we like it or not. We're seeing the rise of electric vehicles into the overall system, as well as some of these switches to the electricity system for industrial processes as well. So that's happening. But the corollary of that means we're going to need a lot more electricity generation. Of course, if we're adding more wind and solar onto the system, as we know, wind and solar does what it wants to do. The wind blows when it wants to blow and the sun shines when it wants to shine. And so we have to integrate that, or we have to manage that variability in order to make sure that when I go back to pressing that light on my wall, that the lights turn on. And so we need to be able to manage that either through backup, which currently is done through having things installed like natural gas, or ultimately adding batteries to the system, or more transmission into the system to be able to interconnect the provinces with each other a little bit better. So we have the ability to pull from one province to another when we have variations in wind and solar. So let's just very, very quickly take some hypothetical numbers. But if we take the data from the first week of January and look at actual performance in Alberta, so at the bottom here, we've got the wind and a little bit of solar. And so the green being, I'll highlight in green here. Here's our wind pattern. So you can see that variability playing out in real time. Now, if we were to scale that system up really, really large, and we're going to scale it wind and solar, and I've underplayed solar a little bit here, given that it's January and we don't get quite as much sun, so it would look a lot bigger in the summer. But nonetheless, you can see now, if I'm going to scale it up on the right-hand side of my slide here, the challenges that may pose to the overall system. We see that variability occurring as a result of the renewables. And so we're going to need to find a way not only to back it up when the wind and the solar is at a low point, but perhaps we also might imagine a time when you've got additional wind and solar above and beyond the load itself. And so we might have opportunity to either charge a battery or maybe export that power somewhere else. So those open up some of the interesting conversations and debates and thinking that's going on in the overall system right now is how do we start to integrate some of these new technologies, whether it's storage into the overall system or how much transmission are we going to need to build out to take advantage of the fact that we have a province like British Columbia, for example, beside us, which has lots of hydro and potentially can act as a battery. And when the wind is blowing in Alberta, we run the wind turbines, and when it's not, we can draw on some of the hydro and vice versa. So those are some of the active debates that are going on. So that sounds easy, that we just borrow each other's electricity, but of course, our current system is much more set up for north-south trade than it is for east-west. In fact, most of our provinces are relatively poorly interconnected to one another. British Columbia sells a lot more power down to California than it does to Alberta, and Quebec also sells a lot more power into New York than it does into its neighbors. And so our current system would need to be rethought. We would need to add a fair bit of infrastructure in order to sort of to integrate the entire country to accommodate sort of the scale of renewables that we might be thinking about if we really did want to electrify everything. And so finally summing up, then if we want to have a lot more electricity on the system, a lot more renewables on the system, we're also going to need a lot more transmission, and so the idea of scaling up, electrifying everything brings with it the idea of a lot more energy infrastructure, whether it's in the actual generation side itself or on the transmission side of things. So some of the work that we're doing at U of A to address some of these questions. I'm doing some of this research with my colleague Andrew Leach, and these are a few of the projects that we've been working on, looking at things like how wind turbines have evolved in Canada over the last few years, what type of transition we might see in the Alberta electricity sector as different policies start to play out, as well as we imagine different technology mixes in the system, how might that impact prices or demand in the overall system? And so those are some of the questions that we're wrestling with as part of the future energy systems. So with that, I'll hand it over. Thanks for your time.